Chapter 3, we're looking at quadratics, and we're going to start out by completing the square. This should be mostly reviewed for you. Completing the square is something that sometimes gets a little bit rusty though. What we're trying to do is rewrite this problem as a quadratic that can be factored into something squared equal to a number. We want to create a perfect square trinomial on one side. So what we have to do is we have to look at that middle term and the leading term and figure out what special number would we need to make this a perfect square. And then we're going to move the constant to the other side. And as long as we add this special number to both sides, we're okay. And the way we come up with that number is we take the b, the coefficient of x, and divide it by 2 and then square it. And that left-hand side is now factorable into something squared, and the right-hand side is just a number. X plus 3 squared, to be precise. It's always going to be the number that we squared to get our mystery value. And then we combine like terms, and now to solve this it's a matter of square rooting both sides. So x plus 3 equals plus or minus square root 7. So x would be negative 3 plus or minus the square root of 7. Completing the square always will work. Always. But sometimes it's going to work better than others. Factoring sometimes works, sometimes doesn't. Completing the square always works. Quadratic formula always works. So the question here is, should we complete the square? Well, this is a little bit different than the last one because we have a leading coefficient. It says 2x squared. And before we could complete the square, we would need to get rid of that leading coefficient. What we can do is we can divide the entire equation by 2. And personally, I wouldn't use completing the square here. I think it's too much work, simply because there's this leading coefficient. And when that happens, when you have that, usually you end up dealing with fractions. And if I'm going to deal with fractions, I would rather do it in the quadratic formula at the end than all the way through this problem. Just lots of places to make mistakes. So we divide by 2, we get x squared plus 2x plus 1/2. And we want to move the 1/2 to the other side and make room for our mystery number. So equals negative 1/2. Now we take the b, 2, cut it in half, and square it. This mystery value will be 1. Now the left-hand side is factorable. The right-hand side we can combine like terms. X plus 1 squared equals 1/2. Now we square root both sides and isolate x. And there we have our solution. Now with a problem like this, you can rationalize this radical if you want, because it's really 1 over the square root of 2, but you don't really have to. It'll be okay if you leave it this way. But just to remind you that 1 over square root 2 is the same thing as square root 2 over 2. We're multiplying the top and the bottom by that radical we're hoping to get rid of in the denominator. So another way to write this might be negative 1 plus or minus the square root of 2 over 2. And that's what we'd end up with if we used the quadratic formula on this problem also. And that's what we're going to look at next. And quadratic formula is something that you should be pretty familiar with. The way it's written here is negative b plus or minus the square root of delta over 2a. Delta is what we call the discriminant, the value under the square root. And if you're familiar with the quadratic formula, you know that delta is going to be b squared minus 4ac. And what the discriminant is going to do for us is it's going to tell us information about how many solutions and what kind of solutions they are. If our discriminant is equal to 0, it tells us one thing. If it's less than 0, it tells us something. If it's greater than 0, it tells us something. If the discriminant is 0, we're not going to have a plus or minus term, so we're only going to get one real solution. It's what we call a repeated root. Graphically, our parabola would be coming down and, in essence, bouncing off of the x-axis. Its vertex would be on the x-axis. If the discriminant is less than 0, we'll have no real roots because we'd be taking the square root of a negative number. We'll be getting two imaginary complex roots. And graphically, what that means is that our parabola will not touch the x-axis at all. It won't have any zeros. It won't have any roots in the real number plane. And if that discriminant is greater than 0, we'll have two real solutions, meaning graphically that our parabola will be cutting the x-axis in two places. In this problem, we don't know the leading coefficient, but I want to know what kind of leading coefficients could we have that would give us a repeated root, and then also what kind of coefficients would give us no real roots. So we're questioning the type of solutions we're going to get. This is a problem where we're going to look at the discriminant. We don't have to find any solutions. We just need to examine their quality. So the discriminant is b squared minus 4ac, or 3 squared minus 4 times m times 2. And for the first part of this problem, we want to know when does that equal 0. So when does 9 minus 8m equal 0? Well, we can solve that. And we can find that m is equal to 9/8. So if our quadratic is 9/8 x squared plus 3x plus 2 equals 0, we will only have one repeated real root. If I want to know how we're going to have no real roots, what I'm considering here is when does the discriminant become less than 0? So for this, I'm looking at when is 9 minus 8m less than 0? And again, that's a simple linear inequality. We can solve this, and we can find that for m being greater than 9/8, this inequality holds true. So when m is greater than 9/8, this quadratic will not touch the x-axis. We will get two real, or two imaginary, complex roots. Now, quadratics are kind of nice in that you can tell some very useful information just by their coefficients. We can know what the sum and product of any quadratic roots are going to be. So if I knew the roots, say alpha and beta, I know what alpha plus beta is going to have to be, and I would also know what alpha times beta would have to be. And we can look at this in terms of the quadratic formula. We'll call alpha negative b plus that square root of the discriminant over 2a. We'll call beta negative b minus square root of discriminant over 2a. Let's look at what happens when we add these two general solutions together. They have a common denominator. And hopefully what you're seeing is that these radicals are going to cancel out. And since we have common denominators, we can squish these together into one big fraction. Combining the like terms, we get negative 2b over 2a and the 2's cancel. So the sum of any two quadratic roots will always add together to give us the opposite of that b value divided by a. The product of the two roots. So we're taking alpha times beta in their general form. the tops are going to need to get FOILed, the bottoms are going to need to get multiplied together. The nice thing about the tops is essentially it's going to become a difference of squares. So we have b squared. The o and the I part are going to cancel out. And then we have minus the square root of delta squared, or just delta, over 4a squared. Now remember what delta is. Remember what the discriminant is. It's b squared minus 4ac. The b squareds will cancel, leaving us with positive 4ac over 4a squared. So the 4's will cancel. One of the a's will cancel on the bottom. And we're going to be left with just c over a. So if we take any quadratic pair of roots and multiply them together, we'll always get the value of c divided by a.